So should we start?
Ready when you are. Yeah.
All right. So, okay. So we're all very pleased to have Soundararajan give a talk today. And his title is Almost All Entries in the Character Table of the Symmetric Group are Divisible by Any Given Prime. All right. Thank you. Begin. Yeah.
Thanks very much, Dinakar. It's a great pleasure to give this talk in honor of Balu's 70th birthday. And the conference itself has been wonderful. The timing is very difficult from California, so I haven't actually been able to attend in person as many of the talks as I would like, but it's very nice that the talks are all recorded, and I've been able to watch more of them subsequently. So this talk is a little different from what I normally do. It's actually more in the spirit of Ken's talk that we just heard. It has to do with the character table for the symmetric group. And it's a result that I proved recently with one of my former students, Sarah Peluse, and it's really following up on work that she did, where we've been able to show that almost all entries in the character table of the symmetric group are multiples of any given prime that you like. Okay, so it's a very classical object. So let me start by describing a little bit about what these objects are. The talk will be mostly self-contained, so you will have to trust that the characters of the symmetric group are interesting, but what properties we need about these character values will kind of just develop as we go along. So the talk is about the symmetric group Sn, and Sn has a number of irreducible representations. The number of irreducible representations of Sn is the same as the number of conjugacy classes of the group, and the number of conjugacy classes of the group is just the number of partitions of n, as we heard also in Ken's talk. You can just think of a permutation and look at its cycle decomposition, and everything with the same cycle decomposition lies in the same conjugacy class. Now, we know how many partitions there are of n. There are lots and lots of them, growing almost exponentially, like exponential of square root of n, with this constant 2 square root of zeta 2, and then with some tame thing in the denominator, 4n root 3. And of course, much more is known about this, that you can even give an asymptotic expansion, which is pretty much exact. And I guess Ramanujan already suspected something of this type, but this was, of course, established later. Now, so there are two ways in which the partitions appear. So you can pick a partition of n, and it corresponds to an irreducible representation of the group Sn. And you can also take a partition mu of n, and it corresponds to a conjugacy class of Sn. You can take each one of these irreducible representation. An irreducible representation, or any representation, is determined by its character. So, which means that on every element of the group, you form the trace of the matrix that you get. And the matrix is, the trace depends only on the conjugacy class. So you can think of taking a character associated to every irreducible representation and evaluating it on a given conjugacy class. So this is a well-defined object. You could evaluate it on any element G of the group Sn, but it's also the same if you evaluate it on a conjugacy class. So that's a very classical object of study, but surprisingly, there was an arithmetic fact about this, these numbers, these traces, which was noticed only very recently in about 2017 by Alex Miller. And if you look at small tables of the symmetric group, like usually one deals with S4 or S5, most of those values don't look even, they will look mostly odd. But if you carry it out a little higher, so Miller went up to 76, where there are already lots of partitions of n, about 9 million of them. So it's not an easy calculation, but he found that if you go to the group Sn with n is 76, most of the character values tend to be even. So about 87% of them are even. And he also computed the number of these that are multiples of 4 multiples of 3 or 9 or other primes. And the data is maybe not so conclusive. So for n is 38, he found 82% are even, but only 63% are multiples of 4, 67% are multiples of 3, and so on. So it's not clear what these numbers are, but maybe these are substantially big, so maybe they're tending to 1. Okay, although it's not clear from here whether this is tending to 1. He also found that a number of these values are just equal to 0. So the number of character values that he found to be equal to 0 was something like 36%. And it's unclear what this 36% means, whether it should actually be a percentage, or maybe it's going to 0, or maybe even going to 1. Probably not going to 1, probably going to 0, but we don't know yet. So based on his numerics, Miller conjectured that the probability of finding an even value of a character goes to 1 as n goes to infinity. So in other words, you pick uniformly a partition lambda of n, you pick uniformly a partition mu of n, and then you evaluate the character chi for the irreducible representation corresponding to lambda at the conjugacy class corresponding to mu. So that divided by the total number that you have, which is the number of partitions squared, that ratio goes to 1 as n goes to infinity. And he conjectured that the same is true for every prime p, not just for the prime 2. And actually, I guess he would also guess that it's true for every number, not just primes, but also holds for prime powers. So Miller himself proved, and we'll see why this is true later on, and it turns out not to be too hard, that if you pick a representation at random uniformly from the symmetric group, and then you pick an element of the symmetric group at random. So you, instead of picking a conjugacy class at random, you pick an element at random, then the character values tend to be 0. They tend to be 0 with probability 1. And the reason for this is that we'll see the reason for it is that most elements of the symmetric group will have one very long cycle. This is a bit like smooth numbers. And so like a proportion of numbers will have a prime factor which is very large. Like half the numbers will have a prime factor bigger than n to the 2/3 or something like that. So most of the values, if you pick the group element at random, are in fact equal to 0. But this changes if you pick the conjugacy class at random. It's a different problem. And previously, John Mackay had computed the number of character values, number of dimensions of irreducible representations that are odd. And most dimensions of these irreducible representations end up being even. And so that amounts to computing the character value at the partition. That would be the identity element of the symmetric group. So it would just be the partition 1 + 1 + 1 n times. And this was generalized by MacDonald, and he computed the number of dimensions of irreducible representations that are not multiples of any given prime p. And again, that's a small number. And these ones you can just compute exactly how many such representations there are. Then there have been some more partial results by Gluck and Moratti and Miller himself in connection with this conjecture, where they proved that certain columns of the character table will have many zeros, and therefore in particular will have many things that are multiples of p. And other kinds of results in the literature, here's one such. These have to deal with special kinds of partitions. Like you start with a partition for some small number, and you scale it up by maybe dilating it to get a partition of larger numbers, and then you study what happens in that case. Or you add a whole bunch of ones at the end, and then see what happens in that situation. So what Sarah and I proved last year is that Miller's conjecture is true for every prime p, that almost all character values are multiples of p. And in fact, you can do this with some degree of uniformity. You can take your prime p to go all the way up to log n over log n squared, and it holds simultaneously for all these primes. So in fact, almost all of these character values are multiples of the product of all the primes up to log n over log n squared. So in particular, it means that if you take a character value, it's either going to be 0 or it's going to be pretty big, at least as big as the product of these numbers, which is not quite n, but it's like n to the, you can get it all the way up to n to the 1 over log n, or you can replace this 2 by a 1, which would be the limit of our method. So this builds on earlier work that Sarah had done, where she proved Miller's conjecture for 2, 3, 5, 7, 11, 13. And then the method that she had kind of broke down at 13 and stopped working. You needed some quantity to be bigger than 1, and it happened up for the primes up to 13 and then stops. So this proof simplifies that argument a bit and shows that it's true. In fact, the method works for every prime p. But what remains, and which we can't handle at all, and you'll see why, is that we don't know how to understand anything about prime powers. Divisibility of these character values by p squared is kind of completely open. And we also don't know anything about how many zeros you have in the character table. That we can't touch. Now, when I gave versions of this talk a couple of times.
Sorry to interrupt. So do we conjecture the same for prime powers?
Yeah, for prime powers also, it's conjectured that it should be 100%. 100% of them are multiples.
I see. Yes. Thank you.
So I gave versions of this talk in December, and then people wanted to know if what if you don't pick the irreducible representation at random, but you just with a uniform measure, but suppose you pick the irreducible representation with respect to the Plancherel measure. So the Plancherel measure is to weight the representation lambda by proportionally to the dimension of lambda squared. So if your representation has large dimension, it counts for more in this. The sum of the squares of the dimensions adds up to n factorial. So this is a probability measure. Okay. It turns out that if you pick lambda at random with respect to the Plancherel measure, the problem actually becomes a little bit easier, and I'll explain a little bit why that's true. That's the case. And in fact, if you pick lambda at random with the Plancherel measure, most of the character values are actually equal to 0 if you pick mu with the conjugacy class with just the uniform measure. Okay, so there's a very funny way in which my guess is that if you pick lambda with uniform measure and mu with uniform measure, then most of the values are not 0. So with probability 1, you will get something non-zero in that measure. But if you pick lambda with another natural measure, the Plancherel measure, then almost all of them are equal to 0. So it matters very, very seriously how you're picking your representation randomly. So now let me say what the ideas of the proof are, including, what these character values are, or how we can compute or work with them. So there are kind of two different ways in which one can think about these character values, and both will be useful for us. One is the Murnaghan-Nakayama rule, which I'll describe a little bit now. And the other is a formula due to Frobenius, which allows you to compute these character values as coefficients of some polynomial in many variables. So the Murnaghan-Nakayama rule allows you to compute these character values recursively. So you have a partition lambda and a partition mu, and it allows you to take one part from mu, remove it from lambda in a certain way, and then reduce it to a problem of computing the character value for a partition with one fewer part in lambda, in mu. So here's how it works. Suppose I want to remove the first part from the partition mu, and I want to remove some of those parts from lambda, and then have some kind of recursive formula like this. Okay, let me try to explain what we are doing in this recursive formula. These rows that we are going to sum over are called ribbons or rim hooks or border strips. And these are, uh, uh, parts like this, like that part would be a border, a rim hook. If you remove this part from lambda, you still get a partition of lambda. Another part that you could remove, another ribbon hook that you could remove would be something like this. If you remove those three parts, then you would still get a partition of lambda left over. And again, you can remove these 5 parts. So what these border strips are is that you move along the border of this partition lambda. So things like this in the border. You never have a 2 by 2 square. So this is not going to be part of any border strip. So the border strip will have to be a ribbon like this, or like that. Okay, or this could be a ribbon, but you can't have a 2 by 2 square contained in your ribbon. So you take a part of length 3. So this is the partition mu. So take one of these parts of length 3 and figure out how many ways you can remove it as 3 parts from lambda. And there are 2 ways you could do this. You could either remove this ribbon, which has length 3, or you could remove this ribbon, which has length 3. And those are the only 2 ways in which you can do that. So if you remove this ribbon, you would be left with this partition. If you remove that ribbon, you would be left with this partition of lambda. And the Monaghan-Nakayama rule says that there's a recursive way in which you can compute these character values by removing all possible ribbons of this size lambda 1, mu 1, say. And then there is some sign that you can associate to that ribbon. And then you just compute the character value of having removed the part mu 1 from mu, and having removed this ribbon row from the partition lambda to get either this partition or that partition. Is that okay?
So is it a double sum? There's a sum over mu1 as well?
No, so it's just over 1 mu 1. Then you recurse on this, right? So then you remove some part from.
I see.
Okay. And then you keep going. You keep going until you get to like just.
But which mu1 you take? Any?
It actually doesn't matter which one you take, but I just said, choose the largest one, for example. So either go in that order, but it doesn't matter which way you choose.
Okay, that makes sense. Thank you.
So, okay, so now the next thing I want to talk about is hook length, which Ken already discussed in his talk. So here's a partition of 19 that I've written down. What is a hook length? A hook length of this part would be the number of boxes that you have to the right of the box, plus the number of boxes that you have below, plus 1 for the box itself. Okay, so for each box you can count so for this one, there are 2 to the right, 1 below, and then the box itself, so that's a hook length of 4. Okay. So these hook lengths are quite important in the study of these representations. For example, the dimension of the representation associated to this would be given in terms of products of hook lengths appearing, 19 factorial divided by the products of all of these hook lengths that we have. Now, the thing to note is that if there is no hook length of size t, then there can be no ribbon of size t as well. And the reason is, suppose I have a ribbon here of length 3. If I kind of push this guy up, then I will see that that hook length has to be 3. Another way to say it is that what would be the hook length if I go along the whole side length of these parts, like so? If I move all of these up, you can kind of see that I would get the hook length of that part, which would be 10. And there would be 10 things in this border here, 3, 4, 5, 6, 7, 8, 9, 10. Okay. This is just from the definitions of the fact that your border strips don't have any 2 by 2 boxes in them. So you just keep moving the boxes, like you move this back, this box here, this box there, this box there, and so on. And then you will see that you will get basically that hook, which will give you that hook length 10 there. So what we see is that if you start with a partition lambda and a partition mu, if you want to remove the partition mu, the part mu1 from lambda, if your partition lambda has no hook length of size mu1, then you simply cannot do it. You cannot remove any border strip of length mu1, and therefore you can't get started on the Murnaghan-Nakayama rule, which means that your character value just has to be 0. Okay. So if you cannot remove a partition of a part of size mu1 from lambda using a border strip, then Murnaghan-Nakayama tells you that the character value is 0. So one thing you can ask is, what are the partitions lambda that have no hook length of size t, or these are called T cores. And again, they came up a bit in Ken's talk. If you look at the number of partitions of n that are T cores, initially this is a very stringent condition because it's very hard to get a partition that has no hook lengths that are equal to 2. This would just be the triangle partition that you can construct with just the partition 1 plus 2 plus 3 all the way up to k or some k. But if you take any number t, at least 4, Granville and Ono showed that there must be T cores for every number n and every t. But initially, these are very rare. So these are the Fourier coefficients of some kind of modular form. And usually they would be pretty small. It's not a cusp form, so it'll have some growth coming from the Eisenstein series part, but it'll be some kind of polynomial in n, whereas the number of partitions of n is e to the root n. So initially, most for small values of t, most partitions are not going to be T cores. But on the other hand, you can imagine that as t gets larger and larger, most partitions are likely to become T cores. For example, of course, if t is bigger than n, then the hook lengths cannot add up to more than n, and everything is going to be a T core to start with. But even way before that, you might start to believe that the partitions will mostly be T cores. Insisting that no hook length should be a multiple of 5 is a very rare condition, but insisting that it's no multiple is nothing is a multiple of something close to n or n over 100, that's a very weak condition. So if t is large, most partitions should be T cores, and you can ask, well, how far does t have to be in order to guarantee that most partitions are T cores? So you can understand this just from the Hardy-Ramanujan formula. If you look at the Hardy-Ramanujan asymptotic formula, that's obtained by just applying the circle method, and you can choose the radius on which you integrate optimally as being e to the minus square root of zeta 2 divided by square root of n. Okay, and then you compute using stationary phase, and you can compute what the asymptotics of this integral are. So if you just think of this as some insight about how partitions are behaving, then to understand when most partitions are going to be T cores, you just have to look at how this generating function is differing from the generating function for all partitions, which is just this numerator here. If that numerator is close to 1, then it means that most of your partitions are actually going to be T cores. So we just have to understand when this, this is the way in which your generating function differs from the generating function for all partitions, when that's close to 1, and then almost every partition is going to be a T core. Now, this is a simple calculation. So if you want this to be close to 1, it's the term n equals 1 that's going to be most important, and then it behaves like e to the minus t times q to the t. So I want t times q to the t to be small, and q is this guy, e to the minus pi over square root of 6n from Hardy-Ramanujan. And then it's a simple calculation to figure out how big t must be. It must be at least as big as square root of 6n over pi in order to cancel this guy. Q to this will have to be something small. And then you have this t that grows like a square root of 6n over pi. To cancel that, I put a log of square root of 6n over pi. But now I get another log of square root of 6n over pi here. To cancel that, I need to put a log of square root of 6n over pi. And then at this stage, I know that I've done enough. Anything with t larger than this is going to be a t-core. Almost every partition is going to be a t-core. Okay. So what this means is that if you have a partition mu, so corresponding to a conjugacy class, if that conjugacy class has one big cycle, if it has a cycle that's larger than this threshold, then you can be guaranteed that almost all of the time you can't make Murnaghan-Nakayama work, and then the character value will have to be 0. Okay. And this is the idea of in Miller's result as well. I told you that if you pick an element of the group Sn at random, then almost all the character values are 0. Why is that? Well, the cycle decomposition of a random permutation looks exactly like the prime factorization of a random number. A random number is likely to have one prime factor which is very big, or a power of n. Similarly, a random element of the symmetric group will have a cycle length, will have one cycle which is very big, almost on the scale of a constant times n. And therefore, mu1 for a random element of the group will have its longest cycle much, much larger than this on the scale of n, and therefore the character value will simply have to be 0.
Is that Erdős-Turán that you were quoting? About the cycle?
Well, for the cycle lengths, I don't know who first did it, but I guess if you say it's Erdős-Turán, I'm happy to.
I just know
I mean, there were people like Goncharov and lots of people who did this, right? So it's the same.
I'm not saying
it's the same Dickman-de Broglie function, which gives you the probability of finding a cycle length of size, n divided by u is like the Dickman function rho of u.
Yeah,
right.
I just know they pioneered this statistical behavior of random elements of Sn. Yeah.
But the question here is not about a random permutation, but about a random partition. So you can ask, what is the largest part of a random partition? And that was studied by Erdős and Lehner. And I think, Gergely, what you're thinking of are follow-up papers by Erdős and Turán, which make some of this more precise. And what Erdős and Lehner showed is that the largest part is of a random partition is about square root of 6n over pi times log of square root of 6n over pi. Okay, so this again is relatively easy to prove. But what this means is that if you take v to be negative 100, then this will be e to some big. So this will be some big number. This probability will be extremely small. So the probability of finding the largest part less than this minus 100 will be incredibly tiny. But if you make it 100 plus 100, then it'll be very close to 1. Okay, so the largest part is very sharply concentrated near this threshold, square root of 6n over pi times log of square root of 6n over pi. And the proof is very easy. You just compute the tail of the generating function for counting the number of partitions and ask what this looks like. Again, when Q is the Hardy-Ramanujan radius on which we are computing the asymptotics for partitions. And it's just calculating the asymptotic behavior of this. So now what you get out of this is that you can show that the proportion of values for which you get the character value being 0 is like, it's not a positive proportion, but you can get it being at least as large as some constant divided by log n. So you can see that if n is maybe like 38 or 76 or whatever I said in Miller's calculations, this is still a reasonably big constant. So this may be like 1 in 4 or 1 in 5, something like that. So that's already 20%. So noting that 30% of the values are 0, you don't know if that 30% is actually a number or if it's just going to 0 like 1 in log n. So the numerical data there is not conclusive at all. Okay, but it's mildly bad news for us. What it means is that the largest part of a random partition is on this scale, square root of 6n times log of square root of 6n over pi, whereas the threshold that we need in order to get the character values to be 0 is just a tiny bit larger by this small amount, this log square root of n. Okay? So that's why we are off by, we don't get a positive proportion of values being 0, just a proportion that goes to 0. However, already this is enough to show that if you pick lambda with respect to the Plancherel measure, then almost all the time the character values are going to be 0. Why is that? The Plancherel measure is weighting the partition lambda with this dimension of lambda squared over n factorial. And the dimension of this representation is n factorial divided by the product of the hook lengths. So because these hook lengths appear in the denominator, what it means is that the Plancherel measure likes hook lengths to be small. Okay, and if the hook lengths are going to be small, whereas the size of the largest part of mu is going to be large, then you see that we will win, and the character values will have to be 0. So there's an extensive study on what a random partition looks like if you don't choose it with uniform measure, but if you choose it with respect to the Plancherel measure. This goes back to Logan and Shep, and independently Bershik and Kerov. And then about 20 years back, this was very intensively studied by Borodin, Okunkov, and many others. And what they found was that if you take a random partition with the Plancherel measure, then the largest part of such a partition is about 2 square root of n. And by symmetry, the number of parts is also typically of size 2 square root of n. So this is very different from what we get from Erdős-Lehner, where the largest part is more like square root of n times a log of n, and the same for the number of parts. But this means that the maximum hook length is really going to be the largest part plus the number of parts minus 1. So the maximum hook length is going to be about 4 times square root of n. So if you pick lambda at random with the Plancherel measure, the largest hook length that you can find is about 4 root n. And so therefore, if you pick a conjugacy class at random, it'll have its largest cycle length be so big that there will be no hook length of that cycle length. And so the character value will have to be 0. Okay, so this is not the result that we are discussing, where the main result that I mentioned was picking lambda with a uniform measure rather than with the Plancherel measure. So to understand that, we need one more ingredient, and this is the other way of computing the character values for these irreducible representations. This is a formula of Frobenius. So you can compute the character value as the coefficient of this power of these variables x1 to xn in a certain polynomial of many variables. This delta is just the discriminant of the Vandermonde, so the product of xi minus xj. And then these are just power sums. So the kth one is the sum of x1 to the k up to xn to the k, with the convention that p0 is just 1. So I've kind of padded the partitions lambda by adding a bunch of 0 at the end so that there will be n parts, so to speak, but the last few parts might be 0. I've also padded the partition for mu with a bunch of zeros at the end. So mu1, mu2, but then n parts, but then the last few might be 0, which are not really figuring in this.
These are called Schur polynomials, no? These are Schur
polynomials, yes.
So why Schur if it's Frobenius? You don't have to answer.
No, I don't know. I think Schur was a student of Frobenius, right? I mean, I mean, Frobenius might have started with some of this, and then Schur would have continued much of the work. This is I have no idea, but yeah.
I think some people say Frobenius Schur.
Okay. And so from So what we want to extract from this formula uh, is that there's a congruence. So if you start with a prime P, and you have a partition mu of n, and you associate now a new partition nu by doing the following. So take in the partition mu, if you see p parts of size m, combine those p parts into one larger part of size pm. Okay. If you do that, then the character value for mu is congruent to the character value of nu mod p. And the proof is easy from this Frobenius-Schur formula. What you have on one side would be x1 to the m up to xn to the m raised to the p, because you have p parts of size m. But that's just congruent to x1 to the mp to xn to the mp, which corresponds to having one part of size mp. Okay. It's also at this stage that it's very important that we only get congruences for primes p, and it doesn't generalize for prime powers, because this formula will not generalize for prime powers. Okay. So now you have a way of combining this formula with the earlier work that we had on Murnaghan Nakayama. Take a partition mu, keep combining p parts of one size into a bigger part of size pm. Keep doing this until you can no longer do it. So in other words, start with the partition mu, keep doing this until you arrive at a partition mu tilde, and this partition mu tilde will have the property that it doesn't contain any part appearing p times or more. Okay. And if you do that, we still have a congruence. The character value at mu is the same as the character value at mu tilde mod p. If you can now show that mu tilde has largest part, which is bigger than the threshold that we want in order to ensure that every partition, almost all partitions are T-cores, then you will know that this guy is equal to 0, in which case you will understand that the character value chi lambda of mu is a multiple of p. So that's the idea. And so now I can tell you the main technical result is to show that one can actually prove this, that if p is smaller than log n over log n squared, again, you can improve this to some constant times log n over log n. So you can remove this log n squared to just a 1. If you follow this procedure of starting with the partition mu and extracting from it a partition mu tilde as above, then the largest part of mu tilde is a little bit larger than the threshold that you get in Erdős-Lehner. That's the Erdős-Lehner bound for a random partition mu, but then you get to multiply this by something bigger than 1 plus 1 over 5p, and this is going to beat the threshold that we want for almost every partition to be a T-core, and then we are done. Okay, so you can see if p is like log n over log n, that's the place where you get a constant times log n, which is the threshold that we need. So most of these partitions lambda will result in a partition mu tilde with a very largest part, and then for most of those mu tildes, the chi lambda of mu tilde will just be 0. It will not be 0 for a very small number of partitions lambda. So why should you expect this? So here's a heuristic for it. Just consider partitions of n where each part appears no more than k minus 1 times. Okay, so if k is 2, then this will be the number of partitions into distinct parts. So obviously we can compute asymptotics for this just as easily as we can compute asymptotics for partitions. You can just look at the generating function, figure out what we should choose q to be to integrate on. And it turns out to be slightly different from the Hari-Ramanujan circle. So by this factor, square root of 1 minus 1 over k. Okay, which in turn means that the number of such partitions is a little bit smaller than what we would get for all partitions, of course. But also it means that in the Erdős-Lehner theorem, if you use this circle and compute the analog of Erdős-Lehner, the largest part of one of these partitions where nothing appears more than k minus 1 times, that part, the largest part, is a little bit bigger, right? It's a little bit bigger by a factor of square root of k divided by square root of k minus 1, by this factor. So if this procedure that we had of going from mu to mu tilde, if it's picking up random partitions mu tilde, we expect to win the game because a random partition mu tilde will have a largest part which is substantially bigger than the largest part of a random partition. Now, this is just a heuristic. It's not true exactly, because what we have is a map from all partitions to partitions where no part appears p times or more. But this map will be many to one. So many guys here will go to the same guy. And you want to make sure that that somehow you're not landing inside a small subset of this, which is not what your typical partition in this set looks like. Okay, so it may not be uniform measure. The push forward measure here may not be uniform on all of these guys. And in fact, it is not uniform, but it kind of behaves almost in the same way. So if it behaved uniformly, we should expect the largest part here to be on the scale of square root of k over square root of k minus 1. It turns out that the constant is off there, but it still behaves roughly like 1 plus some other constant divided by k, a factor of that bigger than the Erdős-Lehner threshold.
So is this mu tilde uniquely determined by mu?
It is uniquely determined by mu, yeah.
Because there are many ways to get to mu tilde.
Yeah, there are many ways to get there, but I think they all lead to the same.
Okay.
It's a kind of combinatorics which I don't want to think about right on the spot.
Yeah,
but
sure,
I think it's a few minutes thought, and I don't think you get. And I'll describe some of what's going on in this process. So what are we doing when we are collapsing these partitions, right? So this is, I guess, really elaborating on Gergely's question. What we are doing is that if you imagine that you have a number k that's co-prime to p, and look in mu at all parts of the form, k or k times p or k times p squared and so on. Look at all the partitions of parts of that type, okay? So if all of those parts sum to k times L, let's say, then how are we getting mu tilde? We're going to combine, if you have, p parts of size k, you combine it to one part of size kp. And then if you have, p parts of size kp, you combine it to one part of size kp squared and so on. So when you're done with that process, you would have some other number of parts of the form k times some powers of p. They will all have to add up to the same KL. Nothing has changed, right, in what we're doing. But now, how can you determine what this partition mu tilde is? You just write this number L in base P, and then that tells you what these parts have to be. And the reason why you write it in base P is that no part can now appear more than P times or more. So that's like writing it in base P, where each of the digits goes from 0 to p minus 1. Okay, so you can read out from knowing what mu is, you can read out what this partition mu tilde is going to be. For every k, just compute all the parts in mu of size k times some power of p, add them all up, then take that number L and write it in base P, and that's mu tilde. So on the other hand, suppose I give you a mu tilde and I want to know how many different mu's does it come from. Well, the point is, okay, so take any number k and again look at all the parts in mu tilde of the form k times p to the j. Now again, this is going to, so any one of these parts can appear at most p minus 1 times. So if these sum to some k times L, then what you want to do is you want to take L and look at all the partitions of L into powers of p, and then every single partition of L into a powers of the prime p will give you one possible way of a partition mu from which you could have gotten this. So that's the correspondence between mu and mu tilde, and we have to do this for every k that's co-prime to p. So if you want to write this in terms of generating functions, so if you think of p tilde of j is the number of partitions of j into powers of p, so that has some generating function, just like with usual partitions. And then what I'm counting here is just all partitions in two different ways. So on this side, this is just visibly all partitions of n. And then on this side, I've done the process of identifying mu with mu tilde that I've just described. For every number k that's co-prime to p, you want to think of all the ways of writing a multiple of k times j and writing this j, partitioning it into powers of p. And the two things are the same. So in generating function, this is the correspondence between mu and mu tilde that I have discussed. So now, if you want to count the partitions where when you combine all the parts, that you get some k times j, j going up to some stopping point, you just take this sum and you truncate it somewhere at p to the r minus 1. So if you do this, then you'll be counting partitions where the largest part in mu tilde is no more than k times p to the r. Okay, corresponding to this k. So that tells you how to get an upper bound on what we want, that when you take mu and push it to these mu tildes, and you want to count how many mu's will end up having a partition mu tilde where the largest part is not too big, you can get an upper bound for it by just writing down a generating function. So I'm going to count here all the partitions where mu tilde has the largest part of the form k times p to the j, which is smaller than this k times p to the r, for every k in some given prescribed set script k, but forgetting about what happens for k not in this set. This will give an upper bound for the number of partitions that I want to count in our theorem. So this is a generating function that you can just work with. You will compare this generating function to the generating function of all partitions, and so you want to study this generating function where Q is the same as in the Hardy-Ramanujan asymptotic formula, giving you the answer for unrestricted partitions. And then it's kind of just a calculation. Maybe it's not obvious how to choose the different parameters in this formula, but it really is just a computation, and you can show that most of the time you will get that the number of times where when you push mu to mu tilde and you don't get a very large first part, that is substantially smaller than the total number of partitions of n. And this in turn will show that most of the time you'll get mu tilde having one part which is larger than the threshold that we wanted, and that will complete the proof. So this last part of it has been a little bit brief, but it really is no more than a computation with generating functions. And I think I should just refer you to the paper. It's not a very long paper. It takes only about 8 pages to prove. And so maybe that gives you some idea of the proof. Well, thank you very much.
Thank you, Son. And are there any questions or comments? Yeah, Herr? No? Oh, okay.
I have a quick question.
Yeah.
So just for curiosity, so in the first work of Sarah, where was the thing that you said that it broke down at 13?
Yeah, so the proof that I've given you is different from the proof, the final part of the proof is different from what Sarah does. So what she did, let's just think of the case for Miller's conjecture for P equals 2. What she did was to look at the number 1, and then she looked at all the times, and combining two appearances of the number 1 to give you a part of size 2, and two parts of size 2 to give you a part of size 4, and so on. So she just followed 1 and tracked it and saw how many times you get a very large part, starting with 1. Okay, and that already is going to be enough to prove Miller's conjecture for 2. And then she did it for other smaller parts for each prime, like 3, 5, 7, etc. She looked at very small parts k and saw how those filtered through in this procedure for going from mu to mu tilde. And she was trying to show that for the different small parts, they behaved kind of independently of each other. Mm-hmm. For the prime 2, you could make do with just one number, but for the prime 3 and more, you need more than one number. For the prime 2, she uses the fact that log 2 is less than 1, but log mm-hmm. 3 and so on is bigger than 1, and therefore the same argument doesn't work for 3. Mm-hmm. So, but when you do the argument that way, it's a difficult matter to show that different values segregate independently of each other. And it turns out that it's not the most efficient way to do it. Instead, what's being done here, it's not so apparent from the description now, is that we are actually approaching the problem from the other side. So what we are doing here is to choose one part which is very large, almost as large as in Erdős-Lehner. Okay, so this is like mm-hmm. almost on the scale of square root of 6n. And then we are just looking at that part and seeing how to combine, that part appearing p times or p squared times or whatever. So in some sense, it's doing the opposite of what Sarah does, and the opposite is more efficient, and you don't see this problem of stopping at p is 13.
Okay, thanks.
Any other questions? I have a quick comment and a quick question. A comment about Schur polynomials somebody mentioned. They were actually introduced by Cauchy in early 1800s, but it was used by Schur to prove the relationship between the representations of Sn and GLN in his thesis. I think that's why it's called Schur polynomials. And the question is, there are also these Weyl groups of root systems. And for AN, it's Sn that you're studying, but the other groups also have the property that all their characters are integral. Have you looked at the divisibility of those things?
So I haven't, but I think there's also work that's been being done by Miller and Larson, and I think they actually also studied. I don't know exactly all the details, but in certain cases they actually prove that a lot of them are 0. But for the symmetric group, a lot of the character values are 0, but for the symmetric group, a lot of them don't seem to be 0. But again, I think that's another question that I would, very much like to understand, but it seems very hard to, my guess is that most of the values here for the symmetric group are not 0, but it seems very hard to even get started on that.
I see. Yeah. All right, thank you.
So
any other? Yeah. Go ahead. Yeah.
Well, I was going to say that as the last speaker, I would like to thank the organizers again for arranging this wonderful event, especially the organizers Adhikari, Shauli, Purushottam Rath, and Anirban. So maybe we can join in a round of applause for them as well.